all the things you need to know about chem, so mysterious, and we're going to learn about nuclear chemistry. All the things you need to know about chemistry. GT school bus, there's no mountain high enough so we can climb them all. GT school bus, our instructors are strong enough, just like hydrogen. Class, ready to go on our field trip? Let's take the magic CT school bus and we're gonna go learn about radioactive decay!
Let's go! I love rocks! I want to know how old they are! When we're on the CT school bus, can we listen to the radio?
Only if it's radioactivity! Okay class, we're here! Time to go learn about rates of radioactive decay. Let's just head over to these rocks over here because I'll teach you some things about them.
Mr. Brune, wait for me! I love rocks!
Some materials contain unstable isotopes, meaning they have too many electrons. Unstable isotopes are radioactive, and they're called radioisotopes.
Oh, that's crazy!
In order to stabilize, an atom that is radioactive must undergo radioactive decay, which causes the unstable nucleus to lose energy by emitting radiation. This process can result in the formation of a new element with a different number of protons.
Misty, I have a question. Does everything decay at the same rate?
Nope, different nuclei undergo radioactive decay at different rates. Some radioisotopes take millions of years to decay, while others take just a fraction of a second. So the ones that take just a fraction of a second, we never can observe them in nature. Radioactive decay is a first-order kinetic process, which implies that it has a characteristic half-life.
Oh yeah, I remember what half-life is. It's the time it takes for a substance to half its yield.
Half-life is constant in a first-order reaction, meaning no matter how small the concentration becomes, the half-life will always be the same. The half-life of a substance is unaffected by external factors like pressure, temperature, and state. That means that if Pranami gets heat stroke and starts to melt, she actually won't decay any slower or faster. Also, pressure. If there's a lot of pressure put on Pranami and she gets condensed, well, that also does not change the half-life at all.
Mrs. Steve, do you know the half-life of these rocks?
Oh yeah, so this is barium-135. Barium-135 has a half-life of 10.55 years. Therefore, after 10.55 years, 10 grams of barium-135 would decay to be 5 grams.
How do you know the calculations?
Let's go to the classroom. Okay, let's practice a half-life problem. 32 grams of forminium has a half-life of 15 years. How much remains after 37 years? Well, let's look at the equation, our formula. The number of grams equals the initial number of grams times half to the power of time passed over the half-life. So we have the half-life. We actually have all the variables. We need to find the number of grams. So N equals, can you try this by yourself? I see you guys working hard. We're almost there. Did you get that 5.79 grams remain after 39 years? You're correct. Good job.
Isn't the half-life of any particular nuclide a constant? Oh wait, doesn't that serve as a nuclear clock to determine like the age of any object?
Yeah.
Isn't that radiometric dating?
Yes, it is. Wait, Adam, Could you tell me about that?
Well, radiometric dating determines the age of geological materials like rocks
And minerals.
To do this, we use radioisotopes and their abundances.
There's another thing called radiocarbon dating, which date things that used to be alive, like wood, fossils, and human remains. The way that this is done is when carbon-14 is used to react with oxygen to form CO2 in the atmosphere, which kickstarts the cellular respiration process. Because a living plant or animal has a constant intake of CO2, they're able to maintain a stable ratio that's pretty consistent with that of the environment. Once the organism dies, it no longer ingests carbon-14 to replenish that which it lost. With this, the ratio of carbon decreases. If we measure this ratio and compare it with that of the atmosphere at the time, we can estimate the object's age. After 50,000 years, this method can't be used because radioactivity is too low to be measured.
I want to know if that rock is older than my grandpa. He's like 142.
Let's figure out how old that big rock is. First, we have to realize that rate equals Kn. K is the rate constant and N is the number of radioactive nuclei. So, how old is the rock? 0.332 milligrams of lead-206 for every milligram of uranium-238. The half-life for the decay of uranium-238 is 4.5 times 10 to the 9 years. Well, first of all, we need to calculate the original amount of uranium that there was for every amount that still exists today. So we can do that by adding 1 milligram, because there's 1 milligram for every 0.332 milligrams of lead, and we can add it by the ratio of lead to uranium. Then we multiply that by our value, which gives us a total of 1.384 grams. So that's the original amount of uranium. The next step is to find the decay constant. Can you find the decay constant? Okay, so the only thing we needed to do is replace T1/2 with the half-life that was given. So with that, we get the answer of 1.5 times 10 to the negative 10 for the decay constant. So the third and final step is to use this equation right here, and we want to isolate for T. So you're going to have to rearrange the equation a little. Then you can plug in the values, and you have your age of the rock. Can you try?
Oh, I know how to solve this one.
Can you come up to the class and show us?
Of course.
Don't worry, guys. I'll walk through it slowly. First, we're gonna isolate the T. So T equals that is your new equation. Now we're going to fill in all the numbers for the equation. So T equals -1 over 1.5 times 10 to the -10 ln over 1.000 milligrams over 1.384, which then equals 2.17 times 10 to the 9 years old. That's how old the rock is. Isn't that crazy?
So kids, what did you learn?
We learned that this rock is 2,170,000,000 years old.
Or in little kid terms, 2.17 times 10 to the 9 years old.